Hello students. So today we will discuss the directive influence of meta-directing group. Here meta-directing group. Remember, say all electron withdrawing groups, they are meta-directing. See, as you know, the groups and substituents are of two types. One is releasing, one is electron withdrawing. So all electron withdrawing groups are meta-directing. Some examples of the electron withdrawing groups are like NO2, can say CN, can say CHO, COOH, SO3H, etc. These are the examples of the electron withdrawing group. What actually happens here? These electron withdrawing groups, they exhibits minus I effect and minus R effect. So what happens? Due to the minus I and minus R effect of the electron withdrawing group, they decreases the electron density at position 2, 4 and 6, and therefore these are also called ring deactivator, because they are decreasing the electron density, means making the ring less susceptible for the electrophilic attack. In this way, they are deactivating, or they are reducing the activity of the ring towards the electrophilic substitution, and thus these are also known as ring deactivator. See, here we will discuss the directive influence of NO2 group today here. See, here it is an benzene ring. In order to explain the directive influence, I am taking here the one of the calculase resonating structure, and in NO2 group there is the double bond between the nitrogen and oxygen, and another oxygen remains linked with the nitrogen by the coordinate bond, and this one is nitrobenzene. As we know that once the coordinate bond is formed, after that one cannot make a distinction between the normal covalent bond and coordinate bond. See, so this structure of nitrobenzene can also be written in this way, N double bond O, and here we may denote the coordinate bond like a normal covalent bond. The only difference is that here is having 6 electrons, that this coordinate bond, the oxygen atom is the acceptor one, while the nitrogen atom is the donor one. So this bond is having a polarity. So here we may write this structure in this manner also. But for the simplicity, I will explain the meta-directive or its directive influence of NO2 group using this structure. See, what happens here? This NO2 group is having a minus I effect as well as minus R effect. And due to these two effects, the NO2 group will reduce the electron density at position 2, 4 and 6, and therefore attack will occur at only 3 and 5. So we are going to show that how this happens. See here, there's the double bond between the nitrogen and oxygen. Oxygen is second most electronegative, so the electron pair of this pi bond will shift over the oxygen. Now this nitrogen has lost its electron, and in order to compensate its deficiency, this will pull the electron from the ring, withdraw the electron from the ring. See, now we'll get the another resonating structure here. Double bond, double bond. Here now, as the two electrons comes in between the ring and nitrogen, double bond will form here. There's a coordinate bond, and now in between the nitrogen and oxygen, single bond will left, and this oxygen will acquire now negative charge. Is it clear? See, in this bond there is the two electron and one of this carbon, one of this carbon. Because this one carbon has lost its electron, will become electron deficient and positive charge. Now in order to compensate the positive charge of this carbon, these two electrons will shift here. We'll get another resonating structure. See here, double bond. As these two electrons shifted here, double bond will form here. This site will become electron deficient, positive charge. Here there's the nitrogen and oxygen minus, and here it is a coordinate bond oxygen. Is it clear? Now to compensate the positive charge of this carbon, these two electrons will shift here. We'll get another resonating structure. Here double bond. As these two electrons shifted here, double bond will form. This site will become electron deficient. Here there's the double bond between the ring and nitrogen. At this oxygen there will be a negative, while there's the coordinate bond and oxygen. Finally, in order to compensate the positive charge of this carbon, these two electrons will shift here. Nitrogen will become electron deficient. These two will come back, and we will get another structure. Here double bond, double bond. As these two electrons shifted here, double bond will form here. Now the single bond will left in between the ring and nitrogen. At this nitrogen, one oxygen is bonded by the coordinate bond, while now double bond will form in between the nitrogen and oxygen. See, as these two electrons shifted here, so the negative charge will be compensated. Is it clear? So these are the possible resonating structures for the nitrobenzene. These are the possible resonating structures for nitrobenzene. Actual structure is none of these. Actual structure lies in between of all these possible structures. Here, actually what happens here, in the ring, a positive charge rotates. Positive charge spreads over the ring. And here, in between the NO2 group and ring, sometimes there's a single bond, sometimes there's a double bond. Means this carbon nitrogen bond is having some double bond character. Okay. Similarly, in NO2, in between the nitrogen and oxygen, sometimes there's the double bond, sometimes there's a single bond. Means this nitrogen oxygen bond is also having some double bond character, and this oxygen sometimes it is having in some structure it is having a negative charge. Means this oxygen is having partial negative charge. This structure is the resonance hybrid for the nitrobenzene. Is it clear? Now, as you know, we must start numbering from the carbon at which the substitution occurs. So this carbon at which there is the NO2 must be counted as 1. See here, this is second position, this third, fourth carbon, fifth, and this one is sixth. Now, if we analyze the possible resonating structures, so we found that here at position 2 and position in the second one here 4 and at position 6, see here, these three sites are positively charged. So therefore, the electrophile, which itself is a electron deficient species, is not going to attack at 2, 4 and 6. Means these 2, 4, 6, 3 sites becomes electron deficient due to the minus I and minus R effect of the NO2 group. So in this way, the NO2 group reduces or the density of the electron over the ring, means it makes the ring less reactive towards the electrophilic attack, and that's why these are also known as ring deactivator. Is it clear? Now see here, now the electrophilic attack is possible only at position 3 and 5, because here's the electron density will be higher at position 3 and 5 in comparison to the 2, 4 and 6. See, so therefore we may conclude that the position 3 and 5, only these sites, they becomes susceptible for electrophilic attack. Means now the attack will occur at position 3 and 5, and as you know, since the position 1, 3 and 1, 5, they are identical, and this one is called meta position. And in this way, the new incoming group, if NO2 group is already existed over the ring, so the new incoming group will form bond at position 3 and 5, and in this way the NO2 group is meta directing. See, suppose here it is the ring, and at this already there is an NO2. Now if this undergoes the Friedel-Crafts alkylation, see here I am taking anhydrous AlCl3. See what will happen here, in the first step electrophile will generate it. Now this electrophile, as it cannot form bond at 2, 4 and 6 because these three sites are already electron deficient. So this CS3 plus will form bond either at 3 or 5, and as these two are identical, so here we'll get only one type of product, already NO2, and now this CS3 will form bond either at 3 or 5, means at meta position, and the hydrogen which will be replaced from here comes out with the Cl in the form of HCl, and in this way we will get here a meta substituted product. Is it clear?